Welcome back to Mechanical Engineering Made Simple. Today we're doing a proper deep dive, a really intensive look into the core physics of structural integrity. Our mission isn't just to skim through definitions. We want to pull out the key insights from a whole range of sources, from basic material science all the way to the complex math engineers use to predict exactly when and why things break.
Yeah, we've gone through a ton of material for this one.
Yeah.
And we've sort of structured it around three big ideas that all lock together. First, just the fundamentals, the relationship between force and how a material actually behaves. So tension, compression, that sort of thing.
Basics.
Right. Then we'll get into how geometry plays a huge role, looking at things like beams and shafts and how shearing forces affect them. And finally, we'll get to the really heavy-hitting stuff, the advanced methods for predicting total failure, bridging that gap from when something just bends to when it completely collapses.
Okay, let's unpack that, starting at square one. The absolute foundation for all of this has to be the concept of stress. Stress is basically the intensity of the force inside a material. So if you have a bar and you're pulling it apart, the tensile stress, what we call sigma, is just the total force, P, divided by the cross-sectional area, A.
And that ratio force over area, that's everything. It's not about the total force, really. It's about the intensity, because that's what determines if the material's molecular bonds can actually take the load.
And as long as that intensity is low enough, the material is in its happy place, the elastic region.
Precisely. That's the linear elastic range where Hooke's law applies. It just means stress is directly proportional to strain.
And the constant that connects them is Young's modulus, E.
Right, which is the ultimate measure of stiffness. For steel, its E value is massive, something like 200 giganewtons per square meter. That number tells you exactly why steel is so incredibly hard to stretch.
And if you stay in that zone, you let go of the load and it just snaps right back. No permanent damage.
As if nothing happened.
But the interesting part, and where the danger starts, is when you push beyond that limit. This is where materials split into two very different camps, brittle and ductile.
It's a crucial distinction. Brittle materials, think cast iron or concrete, they show very little stretching before they just fracture.
They give you no warning. They just snap.
Catastrophically, yeah. But ductile materials like mild steel or copper, they stretch.
Right.
A lot.
They neck down, they elongate, they basically scream at you, hey, I'm about to fail, before they actually do.
Which is why we often prefer them in big structures. You get a visual warning that something is wrong, and they absorb a lot of energy as they yield.
And if you look really closely at a annealed mild steel, the behavior is even stranger.
It is. It's very specific. When it first hits that yield point where it starts to deform permanently, the stress actually dips for a moment.
Wait, it dips?
Yeah, it drops from what we call the upper yield point to a lower yield point. Then it continues to stretch at a roughly constant stress before it starts to get stronger again, or strain harden.
Hang on, that feels backwards. Why would a material get weaker right as it starts to yield? That seems counterintuitive.
It's a phenomenon that has to do with how dislocations get locked up and then suddenly release inside the crystal structure of the metal. We don't really rely on that lower yield point for design, but understanding it is key. It tells you that once yielding starts, it can spread pretty easily for a bit.
That difference between a sudden snap and a gradual warning leads right into how we choose materials, especially when weight is a big deal. Aerospace, high-performance cars.
Oh, absolutely. When every gram counts, we can't just look at strength. We have to look at performance relative to density, which we call rho.
So you get these measures of economy.
Exactly. We define strength economy as the ultimate stress divided by density sigma sub-ultimate over rho. And then stiffness economy is Young's modulus divided by density, so E over rho.
So even if steel has a fantastic stiffness, its high density might mean its stiffness economy isn't as good as, say, a lighter material.
That's it, precisely. And this is why modern composites are such a revolution. Carbon fiber, Kevlar, they have incredible stiffness properties for their weight. Unmeetable, really.
It lets you build things that are incredibly rigid without that huge weight penalty.
Right. And one last thing on direct stress before we move on, initial stresses. Sometimes we stress a part on purpose before it ever sees a load.
Like pre-stressed concrete.
The classic example. Concrete is great in compression, awful in tension. So you run steel tendons through it, pull them tight, and put the whole beam into compression from the start.
So when a load tries to bend it and create tension on the bottom, it first has to overcome all that compression you built in.
It's a brilliant strategy.
Okay, that brings us perfectly to part two. We're shifting from forces that pull and push to forces that try to slide things apart. Shearing stress, or tau.
Right. This is the force acting tangential to a surface. Think of what a rivet feels, or a key in a shaft.
And there's a really important rule here, the principle of complementary shear.
A vital one. It basically says that for any little piece of material to be in equilibrium, a shear stress on one face must be balanced by an equal shear stress on the face perpendicular to it.
Okay, that's a bit abstract. Can you, I don't know, give us a mental picture for that? How does that work?
Sure. Imagine a small cube of Jell-O. If you push the top surface to the right, what does the cube want to do?
It wants to spin clockwise.
Exactly. To stop that spin, you need another pair of forces, a complementary shear. That means the vertical faces also have to have shearing stresses on them to balance things out. They have to exist.
That makes perfect sense. And this shear is critical when we look at bending, which is, probably the most common load structures see.
And this is where geometry becomes paramount. The classic I-beam is the perfect example. Its shape is engineered for one thing, resisting bending.
It all comes down to a property called the second moment of area, capital I.
Yes, and that.
Right, you hear that term thrown around a lot, but what does it actually mean conceptually?
Good question. It's basically a measure of how efficiently you've distributed your material away from the center of the beam, the neutral axis. In an I-beam, most of the material is in the top and bottom flanges, as far from the center as possible. That maximizes the I value.
So for the same amount of steel, it can resist way more bending than just a solid square bar.
Much more. It's pure efficiency.
But that bending also creates new shear stresses inside the beam.
It does. The bending forces try to make the layers of the beam slide past each other. This creates an out-of-balance force that has to be resisted by shear on the cross-section. It's why in a big I girder, most of the shear stress is actually carried by that thin vertical part, the web.
Okay, now let's take that sliding force and wrap it around an axis. Twisting torsion in shafts.
A different kind of shear. If you have a thin-walled tube, the shearing stress is pretty much uniform through the wall. Nice and simple.
But a solid shaft is different.
Very different. The shear stress is 0 at the very center and increases linearly to a maximum right at the outer surface.
And to analyze that, we need a different geometric property.
We do. We use the polar second moment of area, J. It's the key property for anything that twists drive shafts, axles, you name it.
This brings us to our final section, predicting failure when all these different stresses are happening at once. And we have to start with the weak points, the joints.
Joints are always a challenge. They're stress raisers. For a simple bolted joint, you have to check for 3 different ways it can fail.
3.
Yep. 1, the bolt itself can shear in half. 2, the hole can get crushed by the bolt that's bearing failure. And 3, the plate can just snap in tension across the line of holes where it's weakest.
And if you don't design for all 3, it'll just fail at the weakest link.
Always.
Welded joints, though, are a bit simpler to model, right? For something like a fillet weld.
For a fillet weld, yeah, the standard assumption is that it fails in shear across its narrowest section, which we call the throat. It's a reliable simplification.
But what about in the middle of a solid component, far from any joint, where you have tension and compression and shear all happening at once?
Now you're getting into complex stress states, and for that, we need a really powerful mathematical tool. Principal stresses.
Okay, let's pause here because this is a big one. We have forces coming from all directions. What's the core idea? What does this tool let us do?
The insight is this. No matter how messy that stress state is, at any point, you can always find 2 directions at 90 degrees to each other, where the shearing stress is 0.
No shear at all.
None. Those are the principal planes, and the direct stress on those planes, sigma 1 and sigma 2, are the absolute maximum and minimum normal stresses that point is feeling.
So if there's no shear on those planes, where is the maximum shear?
That's the elegant part. The maximum shearing stress always occurs on planes that are at exactly 45 degrees to those principal planes.
And the tool to visualize all of this is Moore's circle.
Yes. It's genius. It takes all those equations and turns them into a simple geometric circle. From that one picture, you can find the principal stresses, the max shear, the stress on any plane you want. It's incredibly powerful.
A great real-world example of this must be something like a pressure vessel, a thick-walled cylinder.
Perfect example. Like a hydraulic cylinder or a cannon barrel, you have a huge circumferential stress, the hoop stress, sigma theta, and also a radial stress, sigma r, both acting at the same time.
And those stresses change as you move from the inside wall to the outside wall.
They do, and we use a graphical tool called the Lemay line to analyze that distribution. It's essential for things like shrink fits, where you heat up one cylinder and shrink it onto another. You have to know those stresses precisely.
Which finally brings us beyond the elastic limit. Let's talk about predicting ultimate collapse when things go plastic.
Right, here we use different tools. One is the principle of virtual work, which helps us solve problems for both elastic deflection and, more importantly, for plastic collapse. For a mild steel beam, total failure doesn't happen when one little spot starts to yield. It happens when enough sections of the beam yield completely, forming what we call plastic hinges.
And a plastic hinge isn't, it's not a physical hinge you install, right? It's more of a concept.
Exactly. It's a point where the entire cross-section has yielded so much, it can't take any more bending moment. It just rotates like a hinge, allowing the whole structure to deform.
Get enough of those, and the structure just becomes a mechanism and collapses.
That's the failure mode.
And there's a term for the safety margin between the first yield and that total collapse, isn't there? The shape factor, S.
That's right. It's the ratio of the full plastic moment, M sub P, to the moment that causes the first yield, M sub Y. For an efficient shape like an I-beam, this ratio is greater than 1, which means there's a built-in reserve of strength. It's a key part of modern design.
So we've really connected the dots. From a single fiber being stretched through the smart use of geometry to handle shear, all the way to these advanced models that predict complete nonlinear collapse.
It just shows you that structural design is this amazing synthesis of physics, material science, and pure geometry. Mastering these fundamentals is what lets you design things that are safe, efficient, and light.
Absolutely. And as a final thought for you to chew on, think about rotating disks.
Oh, good one.
Things like high-speed turbine rotors or flywheels. The centrifugal forces create intense radial and hoop stresses, both at the same time.
And if those combined stresses aren't calculated perfectly, especially at top speed, the whole thing can just shatter. That theoretical understanding of stress that we talked about with the Lemay line is literally the only thing preventing catastrophic failure in so much of our high-speed machinery.
If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.